Welcome to this explainer. Today, we are going to unlock something absolutely fascinating, the hidden, elegant language of advanced physics. If you've ever looked at the sheer chaos of the universe and wondered if there's a cleaner, more profound underlying code to it all, you are in the right place. To understand exactly where we're headed, we kind of have to look at where we've been. On one hand, you've got Newtonian mechanics, the physics of forces and vectors. It is incredibly useful, but let's be honest, it gets messy fast. You have to track 3D directional arrows for every single force acting on every single particle. But on the flip side, we have advanced mechanics, which uses energy and scalars. Instead of all that directional complexity, we use smooth, directionless simplicity to model the universe. It is a complete paradigm shift in how we calculate motion. Okay, let's dive right into this. Here's our roadmap for today. First, we'll look at moving beyond Newtonian physics, then check out the classical mechanics roadmap. After that, we'll meet the Lagrangian, dive into its properties, explore a really cool non-uniqueness loophole, and finally, wrap up with some essential books for mastery.
Section 1. Beyond Newtonian Physics, a New Language.
To truly understand the universe, we have to move past basic physics that relies just on tracking individual forces. We need a framework that actually speaks the language of space and time symmetries. Think about it. Why should momentum be conserved? Is there some fundamental principle, kind of like energy, that just inherently answers this? When we recast mechanics into this advanced language, we're hunting for a foundational action principle that dictates how a system evolves over time. We aren't just calculating where a ball lands anymore. We're asking why the fundamental laws of physics actually demand it lands there.
Section 2. The Classical Mechanics Roadmap, What We Can Solve.
Before we get completely lost in the heavy math, just look at the incredible cosmic and microscopic phenomena this advanced framework unlocks. We get the tools to solve symmetries in time and space, then move right into small oscillations and normal modes. We can tackle central forces, which literally means we can solve the Kepler problem and map out the orbits of the solar system. Add to that scattering and even the crazy complex motion of rigid bodies spinning in space. Now sure, we are skipping relativistic mechanics in this specific framework, but we are gaining the absolute best tools to solve the most beautiful classic problems in the cosmos.
Section 3. Meet the Lagrangian, the hero of advanced physics.
So how exactly do we pull all of this off? Well, we use the absolute core tool of our explainer today, the Lagrangian. It is this incredibly elegant mathematical solution to all those messy vector calculation problems. We denote it with the letter L, and it's simply defined as the kinetic energy of a system minus its potential energy. That's it. I know, it looks deceptively simple, right? But seriously, anchor this in your mind. This one little equation is the foundation for everything that follows. Instead of hunting down every individual force vector, we just look at the overall kinetic and potential energies of the system. Now here is the absolutely crucial part. The Lagrangian is a scalar quantity. Why does that matter? Think about the superpower of scalars. They are completely directionless. They literally do not care about direction. Since kinetic and potential energies are scalars, the Lagrangian is too. It is completely invariant under rotation. You could turn your whole coordinate system upside down and it wouldn't matter. It completely frees us from tracking those messy 3D directional arrows for every single particle in a complex system. Section 4. Properties of the Lagrangian additivity. All right, let's see what happens when we're dealing with a massive system. Imagine a giant, isolated box just filled with moving particles. Step 1. Let's conceptually group them into part A and part B. They're sharing the same space, but we're categorizing them. Step 2, and this is the vital one. We assume the particles in part A do not interact with the particles in part B. They can mingle within their own groups, sure, but A and B do not talk to each other. Because of this, their potential energies are completely separate, and that brings us to step 3. We can confidently conclude that the total Lagrangian of the whole system is just the Lagrangian of part A plus the Lagrangian of part B. Because those isolated parts don't interact, their kinetic and potential energies just elegantly add right together. Section 5. The non-uniqueness loophole, a mind-bending twist. Okay, this is where things get genuinely mind-bending. Let me ask you something. Can two completely different mathematical equations describe the exact same physical reality? In basic math, if the equation looks different, the outcome is different, right? But in advanced classical mechanics, the answer is a surprising yes. It's a highly counterintuitive property that completely flips how we think about equations describing reality. Here's the secret. The Lagrangian is not uniquely determined. If you hand me a system, there isn't just one single magical Lagrangian for it. If you have a Lagrangian, let's call it L,
you can create a totally new one, L prime, just by adding the total time derivative of a new function, f. And here's the kicker. Both L and L prime will describe the exact same system and spit out the exact same equations of motion. It is a literal loophole in the mathematics of the universe.
But hang on, there are some very strict rules to this loophole. This new function f can depend on generalized coordinates, which we call q, and it can depend on time. But it can never depend on generalized velocities, or q dot. That is the ultimate boundary condition. If even one velocity variable sneaks into that function f, the whole loophole completely collapses. And to prove why this works, you just take that new term, df/dt, and plug it right into the Euler-Lagrange equations, the core equations of motion we use in this framework. When you crank through the calculus, a beautiful thing happens. Since f doesn't depend on velocity, taking a partial derivative with respect to velocity just gives you 0. As you work it out, the first term literally cancels out the second term perfectly. The extra math just vanishes into thin air, leaving you with the exact same equations of motion. You completely change the equation, but the physical reality remains entirely untouched. Section 6. Essential books for mastery. The Arsenal. If you want to truly master this beautiful mathematics, you're going to need the right arsenal. Let's walk through a lineup of absolute legends in physics. Because really, there's no substitute for a great book. First up, Goldstein's Classical Mechanics is the standard, your essential starting point. Want something incredibly concise and fantastic? Landau and Lifshitz is a total classic. If you're looking for a nice balance of the historical and philosophical development of these principles, Lanczos is your go-to. Hand and Finch offers a really beautiful modern take on analytical mechanics. And finally, if you want something highly advanced and rigorously mathematical, V.I. Arnold's text is absolutely unparalleled, though it might be pretty tough for absolute beginners. But then, there's 640. That is the exact number of pages in L.A. Parr's book, A Treatise on Analytical Dynamics. It is a massive, exceptionally well-written, incredibly comprehensive behemoth of a book. If you are truly brave and want to dive 640 pages deep into the math we discussed today, that is the ultimate challenge waiting for you. To wrap up our explainer today, I want to leave you with a bit of a provocative thought. Up until now,